Next, we have Scott Yockel from Harvard University. Scott joined Harvard Research Computing in February of 2015 as senior team lead of HPC. He joined the Harvard Residence having been on both sides, eyeballs. Having been on both sides of HPC as a researcher and administrator, he values the importance of providing efficient and streamlined computing resources that expedite the process of scientific breakthroughs. His research domain expertise is in computational chemistry with an overlap of materials science and mechanical engineering. Lustre deployed 3 different ways to meet researcher needs. Scott Yockel. Please right this way.
All right, good, this is on. So my first LUG was back in Austin. And at that time, I had just learned what Lustre was. So coming to a LUG and learning in depth about file systems was pretty impressive. That was Lustre 1.6. So excited to see how much progress has been made. Today, I'm going to talk a little bit about what we've done over the previous year at Harvard. We have about 20 on the team. James Cuff, who's up towards the top left, is the Dean of Research Computing for us and our extraordinary lead of creative ideas, more or less. And I came to this group about a little over a year ago, and I thought, wow, I'm going from one HPC management position to another, more or less, but wow, did I learn. We do so much more in research computing than HPC. So Odyssey is the name of it's like a general name for our cluster. This little cartoon character in the bottom is OddyBot. We have like a bot chat service. So his image shows up all over our web pages and stuff, and people can click on him and talk to him. I hope someday to create an artificial intelligent bot that answers all those frontline questions, at least the first 3 questions. So generally, the more complex part of our setup is that we're in 3 different data centers spread apart by about 100 miles. So that's a really big networking challenge. You have VLAN crazy and ACLs all over the place. In all, it's a fairly large setup with about 60,000 cores. Not all of those are the compute cores. That's just like every core that shows up when you look at something like Ganglia. I think in the compute side of things, we're close to about 50,000 cores in compute. I thought we had 100,000 cores when I turned this in for GPU, but apparently we have like 1 million. It keeps growing rapidly. And then just this year, we went from about 11 or 12 petabytes to 25 petabytes. About half of what we have now is Lustre. We added a lot of Lustre stuff in the past year. I learned more and more about all the NFS stuff that we have. And Isilon we use as our home directory. We call it like our crown jewels storage. Predominantly because it has snapshotting, so like it's a deletion protection type setup. People can go and they have 2 weeks to find their deleted file. And then we have this other thing called Gluster, which I just realized I spelt wrong because I'm so used to writing Lustre and just put a G in front of it. So Gluster, originally we were, like when Gluster was young and before Red Hat had it, we are on the, James is on the board for that file system. So we had a lot of push to adopt Gluster. It has some good features like replicate on write and some of those types of things you would want for people's lab storage. So we invested a lot. And so we have a huge amount of Gluster. And slowly, since I have joined the group, we're going to change Gluster to probably mostly none and Lustre to be mostly take over that space. Just because we've gotten ourselves into problems with Gluster. The healing process is kind of slow when it goes into that state. We just had one, and it was, little did I realize all of our VM infrastructure was sitting on top of Gluster, and so it made a really complicated setup for healing all of that. And I applaud you guys for how well you're maintaining your code to keep Lustre clean, and our Puppet code that runs all of this stuff is very unclean. It's gone from long ago, like the early generations of Puppet 2. It has all sorts of stuff in it that you shouldn't do because there's better ways to do it now. And so we have this huge push to try to clean up things to make it more agile. Because really, there's only about 5 guys in that group of 20 that are like really hands-on, most of the time into the Puppet code, like vowels of our Puppet code. And because we're at Harvard, every professor famous once a VM, right? So we have 300 to 400 VMs. These are running all sorts of stuff. So essentially, research computing is anything that central IT doesn't do, we do. Or anything that they're too slow to do, or not agile enough to do, or too scared to do, right? So we have VMs that are running, monitoring fish tanks, all sorts of stuff, monitoring feeding schedules for laboratory animals. And I mean, we shouldn't be research computing doing billing and purchasing and stuff, but we get involved in that somehow. So that's the VMs that are beyond just research. So just an example of like how much churn do we have on our compute cluster last year, 240 million CPU hours, 25 million jobs. So in a given month, or we could have, I think we have about 600 active unique users running jobs over the course of a month. In any given week, we could have a single user run 100,000 jobs or more, which is pretty frustrating because they could be doing more per task instead of using the scheduler to be their embarrassing parallel setup. So with that, there's the complexity of, do they use CPU right? Do they use memory right? And then, of course, do they use disk right? Okay, correctly, I should say. So the outline of this talk is really to talk about what we've done in the last year for 3 different deployments. So we have 2 different enterprise-level IEEL deployments, both 5.6 petabytes. So that's a pair of MDSs, and then it's 8 OSSs in that setup, on each individual setup. And so there's 2 exact systems, and you'll see in a second why. One's called Holy LFS, and the other is called Boss LFS. So all of our Lustre file systems get an LFS tag to them. We have the bulk of the talk I'm going to talk about is the FLASHLFS stuff that we just recently deployed. It's an all Flash-based system, and then how we've started using Lustre as our target to back all of this stuff up. And then sprinkled throughout, I'll talk about the setup, the testing, and different issues. So when I first came, we had NFS Sprawl. I was overwhelmed when I went to one of the data centers and was like, the entirety of that data center we have for storage because it's a little bit closer to get to from campus, and there's nearly 8 petabytes of it. Of that 8 petabytes, there are 2 petabytes of stuff that is about 5 years old and not on warranty. And coming back to a lab who doesn't have that grant anymore, say you need to like re-up and buy some new equipment, is a difficult situation. And so when we had a refresh of our Dell contract, like our lease contract, instead of doing compute, which wasn't, at that time, didn't seem like it was going to buy us a lot, we decided to leverage and do the storage buy. So just throwing that out there, that there's some flexibility in if you get involved in these lease contracts, you don't have to do what you did 2 to 3 years ago when you were speccing this out. You can change it up quite a bit, and the finance team has to figure out all the details. You don't have to figure that out. Like, go for the technology that you think is most useful for what you need. So at the time, we had 1 petabyte of scratch storage that was IEL, and we have a 90-day retention on that. We cannot keep that thing like lower than about 85% capacity. So, and there's people parking stuff there. There's exclusion lists. It's ridiculous. So obviously, we needed more storage, and so this is what we chose. So one of these setups, so neither one of these are designed to be scratch storage. So because of that, we have hot spares. It's kind of it's a bit of a waste, but we have a whole OST per rack, more or less, as hot spare. Predominantly because one of these file systems, the Holy LFS, is in Holyoke, Massachusetts, 100 and something miles away. So if we have a drive failure, you don't have to wait till you get there the next day for the rebuild to start. You want that to already have done its work, and all you have to do is just switch out the drives. And so the Holy LFS idea is for persistent research data. So this is all these informatics, the climate modeling, seismic modeling, all of this where they're reading in volumes of huge amounts of information, and a lot of the stuff is downloadable from some external database. Get a lot of that storage out of their lab storage, right? Because if you're running, even if you just launch 100 jobs off of an NFS storage, right, a single user, you're just going to bring that NAS running down, even if it's 10 gig connected, because you really can only get about efficiency of about 4 times the number of cores that you have. That's about how much NFSDs you can handle without bogging the server down. And so we have all of these emails in Like, I don't understand why all of a sudden it's taking this long for my job to run, and it ran this long this last time. It's the same type of job. And so we started looking, and a lot of it's because you have a lot of overlap of labs pulling their data off their lab storage because it's too hard to fit in their home directory. And even if they're going to pull it off and then park it in the scratch storage, it's still a really time-consuming process, to do some of that kind of stuff. And you have hundreds of people doing this. So that's the persistent data. The other aspect of this that I'm trying to do, and it's starting to become more and more difficult, and this is the things we've talked about a couple times, the education. Trying to teach people when they're going to use the persistent data setup, teach them about striping, teach them like how to do things efficiently, right? Because in our storage that's the scratch, it's just default one OST to stripe your file, because there's a whole swath of different type of workloads. It's TCP mounted as well as IB mounted. It's TCP mounted 100 miles away to some of the old compute that's at the old data center. And then in Boston, we have this data which will replace some of the NFS stuff, is also for instrument data processing. So we have all of the instruments that are in all the core facilities, we back the storage for all of it. And so a lot of those have pipelines of processing the data, whether it be image analysis for microscopy or informatics or any of those types of gene sequencing type stuff. So here's just kind of an overview to try to clue you into how we're using these systems. We also have LNet routers in front of these. So the data center is one of the data centers, the one that's in Boston, is we have a direct connection to I2 with our 100 gig router. We're currently installing a couple of 40 gig connections to those. We're going to set up Globus. I'm glad to hear a lot of people are doing that. Like, we should have done this a while back. We have a lot of people who use Exceeds. They need to transfer this stuff in and out. Another thing that I've learned from like the NIH and NCBI, some of those databases are that you kind of get rate limited by the number of connections they'll let you have. And I think predominantly that's per IP address. So if you launch 24 threads on a 10 gig connected machine, I was only ever getting 5 gig connection pools, like 5 different threads to 5 different NIH machines. So having a whole suite of clusters with a different IP space might help pull that. So the idea is that one of the data centers, so let me highlight the two of these. So the Holyoke setup is 100 miles away. So the idea is that if you want to put, and that's where all the majority of the compute is that's been installed in the last few years is in Holyoke. All the older compute that the PIs own is still in the downtown Boston data center. But that's where our connectivity is. This Holyoke is nice because MJHPC is on hydroelectric power. It's much cheaper than what you would get in downtown Boston for power. So transferring back and forth with the LNet routers, we have our own 20 gig connection between the two. So the idea is that we'll map your LFS storage straight on the Globus SharePoint. So you could pull stuff in directly onto it, pretty close to 20 gig connected, straight onto LFS. So in one swath, you can pull it in. Instead of dropping it onto BossLFS, transferring it again, because at that point, if you're doing it twice, you're essentially cutting your bandwidth in half, right? So then it'd be like you could have just 10 gig connected out of the Holyoke data center to begin with. So here's one of the things that I've heard a little bit about, and so one thing that's hard is that you have these projects in mind, and you think, okay, this seems straightforward, we're gonna do this, and then some professor writes in, they're really unhappy, you think they're gonna abandon ship, I get the email sent to me, go help them, like go make them happy again. So all of these project things always hit walls, it seems like once every 2 weeks, and then, so the idea is that all of the NFS storage, they're used to having these Samba mounts to their Windows desktop, right, or SIFShare or something like that, or on their Mac. Like, they don't want to have a Linux box necessarily, a Lustre client or something like that in their lab. They want to be able to have this like really nice flexibility. So this idea originally came up because we were having problems with our Gluster Fuse setup and mounting out. We'd have individual labs and their crazy setup using the SMB share, like overwhelm the one server that was serving out Samba. And so one of the guys was like, well, I was like, can't we just like containerize this stuff? And he was like, yeah, actually we can create a Docker container farm such that if that SMB container goes down, it will pop up on another machine. I was like, well, that's also great because then you can just take down a whole machine to do maintenance. You don't have to do anything, it'll automatically migrate. So in this idea, the Docker box, which is the server, will have Lustre mounted, and then you'll expose just that lab's share into their container, and then use like all of our stuff is authenticated via Windows AD, and so we'll have an open LDAP inside the container to map the UID stuff. So it bloats the container a little bit, but that seems like the way to go. So that's kind of an overview. So the next part is a little bit about testing. Sure, you get IEL, they come in, it's an appliance, they deploy it, all fun and games. You run a couple of tests, no big deal. You can see, your 30 gig, where are we, like 32 gig reads and write, or 32 gigs reads. We were like 12 gigs for the writes. This was slightly better than what we had before on a scratch file system. Started doing MD testing. It is a little bit of a chore to figure out the right mix of what you need to hammer the MDT with the right number of nodes and threads. And then I found out after I started really pushing it and I started getting up to like the 150 range, 200 range, then all of a sudden this thing would happen. This is what I call the Stonens shootout. And it was bizarre. I was like, okay, what just happened? Like the MDS just shut off. Like it just rebooted. And then right afterwards, the other MDS would come up. The MDT would transfer over. 2 minutes later, bam! The other guy shoots the other one. Comes up, shoots the other one. I was like, oh my. And so this is really problematic because we have users that will launch like 200 jobs, each job reading the same 60 BWA files. We've seen our scratch file system like pegged at 200,000, like for a while, and had to like go and click on the stuff and figure out whose jobs are doing that. So it's a very real situation that we get into. So sending in a ticket was working, and Oleg was able to like point out, hey, look, looks like you're running over the threshold for the wait time for CoroSync. And so then I started looking at like some ganglia graphs and looking at the loads. And so when we get these load spikes about 2x more than the number of cores, what's happening is that it's pretty simple. It seemed complicated at first, but it was like the wait time for which CoroSync would say, are you there, was just not quite met, right? And so all we needed to do was go in and we just doubled the token that's in the CoroSync comp. So it just gave us just a little bit more time so that it could handle all those threads. It could also handle, you're queuing up that request with all of the write requests. So even if you deploy an appliance, you still need to test it. That's kind of the take home there. So after that change, was able to load it up and to be able to see upwards of 320,000 IOPS. So that's like close to 1 billion files being made. And as you can see, this is like 5 different runs of it. So really, if you look, it's 1 billion files getting made within just a few minutes. That's pretty impressive. Like that's phenomenally impressive, I think. So that's our IEL deployment. So we made that little tweak and put it into both our data centers. And then the next start is the Flash setup. So last summer, into the capital year, we had some extra money. We decided, we've been talking with Intel. They had these Flash devices. Cool, yeah, let's buy 16 of these and build something with it. We'll have a super fast local scratch for people. So each one of these nodes has 2 of these P3600s in them. So it's 4 terabytes on each node. And then I started to think like we needed to do something more creative than just make this 16 nodes for compute. And then like Zhiqi, after he was in town for another thing, he came by and just visited, and we were chatting. He was like, oh, like we're playing with doing this all flash type of Lustre thing, and so we decided to start looking at that as well. And then the guys in my team that are the DevOps guys, I started talking with them. I was like, let's do something creative where it's kind of more on demand. Like we wanted to make, it could be a compute farm. So we have a set where we can just roll it out. Okay, you need a couple compute nodes. This works well for people like if you have a database or something that you want to do really crazy IOPS for. But then we also wanted the ability to do it in a Lustre deployment. So this is totally scratch. So there's no HA, any of that kind of stuff. So this would be 1 MDT, right? And then 15, I should say 1 MDS and 15 OSSs. Or you could say some combination, right? If it was crazy IOPS, you could roll multiple. So the idea is that with this, we could, with the deployment of Puppet, which we're not quite fully there yet, I thought we'd be at that point now. But once we are, I'll publish the way in which we're doing this. Predominantly within the hierarchy file that you're defining some variables and stuff, we'll define the type, and it will roll and drop off the script that would run, that would create the file system, all that. Right now, we're at the point where it does that, but the flexibility of jumping back and forth is not quite as fluid as it can be. So it was a little bit of a build challenge. We had these things last summer, and in the fall, we started messing with them. These devices require kernel 3 space, and then back then, like last summer, like the Lustre 2.7, when you look at the list of support for the server side, right, it didn't support kernel 3 space yet. And so back in, I think it was in December, when we like really started doing this stuff, we pulled the latest setup from Lustre and started playing with it. And basically it works, but there was just a couple of little build things here and there that weren't fluid that we had to like, kind of fix. So the prep work was, so I must say that the build process of this was all done by Justin Riley in our group, who's the team lead for cloud infrastructure or software infrastructure. He came from MIT he's the guy who built that star cluster setup. So he just went deep diving into this, knew nothing about Lustre, nothing about the InfiniBand stack, and so I kind of just like, well, these are the steps, and he was able to like hammer through this in a few weeks. Anyhow, so that's the standard setup to get your kernel, and then the next step was to build the OFED. We actually probably had more problems with building the OFED than you should. You can't just generically download the Mellanox setup and say install everything, because then when you go to build the RPM, it ends up building bad dependencies because it installs RPMs and things that you don't necessarily need. So we had to fiddle with that for a while. And then once we had that, then we were able to go to the Lustre side of things. So we have our kernel and all that's been patched. And then this is the point where we pulled the Lustre release. There was some dependency in the Lustre spec that it was looking for, like the LDIS FS progs, and we had E2FS progs. It was just really a naming change. And then the standard config with your O2IB stuff. So it worked. It was nice. And so it gives you all the description here of the kernel, exact version, and the exact version of Lustre that we had. And this was like the pull request numbering. So then the more complicated part was getting this all to be publicized and the configs to be laid down. So first I'll just talk about the write speeds and the read speeds of the device itself. So this, every time we get a new shiny toy in, James like jumps on it and starts hammering on it. So this is like one of his of DD tests. So essentially this is the write test. So this is stuff being dumped directly from a RAM disk onto the device. Right, so single thread, multiple threads. So you can see as you get to 4 threads, then you've saturated the write capacity. So this is the write across 2 devices, right? So this device is striped at this point in the test, right? So this 3.6 is a number that I'll be talking about later. That's the maximum that any OSS can receive and write data, right? Because when we build the Lustre setup, we have 2 OSTs. We don't stripe them. We didn't really see very, very little difference if you striped it or if you didn't, as far as the aggregate performance of the 2. So, and then the read test. The read test, you start to see quite a bit of difference in variability. When you get to multiple threads, the first one will always be much, much faster because you're essentially reading that one and like cache and memory, that kind of stuff. And then the subsequent ones are much slower. So as you can see, the reads, you can get up to like 6.9. So that's obviously the threshold in which you would have at the IB if you were doing this remotely. Okay, so we built, this is now a test of IOR across 13. So I'd loaned a couple of these out, so I never got to the fact I could test these with all of all of the devices. Anyway, so let me speed up a little bit here. So the take home here, one client, 13 OSSs, able to get really good performance, 6 GB or up to reads. Then I did multiple. So it's multiple clients against you know, the whole of the OSTs. And you can see performance just drops off significantly. You can see this is the UFM UI interface for the received, and you can see it just drops off, right? I should be up much higher. So I talked to Zhiqi. He was like, oh, why don't you try some of these tweaks? So these are all the tweaks that we worked with. Why don't you start looking back? So I was excited, so I started with IOR instead of started with, you know, the LNet stuff. So then we started running LNet tests. And so here's LNet test 101. You can see it takes about, you know, 6 or 8 threads in order to get to the max. The max looks good. We run it with 10 clients on 10 OSSs. Just dropped off to 2.2. So what is happening here? This was a hard lesson. There is a crazy amount of IB congestion in our setup, right? I had to do a lot of analysis. We retooled a lot of the way things were plugged in. Even at that point, it's also started looking at the IB congestion when I'm running these. So this is at the bottom, all the different OSS nodes. You can see there's a couple lingering at the slower speeds for the LNet test. You can see that's the congestion of those particular ones. They're kind of overlapped, so the colors are not showing up there. So you're at the bane of the number of IB switches that you can talk to, more or less. Because we have one core distribution switch. A lot of these chassis have a mezzanine card. And then there's a bunch of other like pie box type style things with GPUs in them that all have top of racks, and we even have some things that are further out that have to aggregate to top of racks before they go back to the core. So you have to be really choosy about how you're doing your connectivity. The other thing is we have only a handful, a few hundred nodes, I would say, that are actually FDR. The rest of these are older nodes that are AMD nodes that are FDR10 connected. So finally, after I learned all this and pushed out and spread out the load across the IB topology, I was able to get you know, like 41 gigs writes, 42 gigs reads. And so just as a reminder of the number of devices, the write max would have been 44.2. So we're like at 93% of the capacity of what the cards can actually do. So like that's pretty good. Like so remotely, and there's a lot of flexibility in that setup because you can change the different types of you know, compute that's involved instead of just having those 16 nodes only. So I just kind of, this is to show you that like with this type of setup, with newer devices, NVM devices, if you're really careful with the way the IB setup is, you can get, you know, 90, 95% of the capacity of those drives or the capacity of the network. So quickly, the last thing. So this is just a picture of our NFS urban sprawl on the left. And then we have to back this stuff up. So originally when I came, we were playing this, like there were 2 or 3 guys that were playing this stupid Tetris game all the time. Lab would want to expand their NFS share. Now it doesn't fit on the backup target. We'd have to move them to a different share or to a different backup target. There's all this moving crap around. And they were just spending hours of a day, every day doing this. So one of the guys was like, hey, Lustre seems to be working well for us in other instances. We make all of this one Lustre namespace. Now we don't have to do that anymore. But now we created new problems. So they did this. I just kind of like, all right, now we have that. So this is disaster recovery backups 100 miles away. Every single NFS file system every day has to be backed up. Here's the big kicker. The entire MDT must be parsed every day. This is almost 1 billion objects. All right, the inodes is like 950 million. And we still have one more of these guys, of these deep systems. We call these like our deep storage. We still have one more of those to roll in, right? So the one thing that's kind of cool about this is that this is old, janky storage. Right? This stuff is off warranty and old. But because the flexibility with Lustre and putting it on all sorts of different types of stuff, some of these have, you know, like multiple OSTs, you know, set up. Some of these have 2 OSTs setups, you know, on each of these. So you have some flexibility because the file system is that robust now. You know, you can have some failures. You can have some things drop off. We can add, you know, capacity as we do it. and rebalance. So quickly, we use Rsnapshot, and so basically Rsnapshot has multiple different directories that are linked. You remove the oldest one, you move the stack up, there's the CPAL, so you're basically just linking all this stuff, and then you rsync the new setup. Thanks to some stuff we found, like there was a thread that Andreas had talked about, didn't realize that the remove was a file stat operation. This, using some of these LFS commands, helps remove some of those strains. And then using the LFS command in the CPL, it also helps speed things up a bit. And so the basis problem was that in the group, there was a lot of guys hand-waving, oh, this is what's wrong, this is what's wrong. And I was like, we don't know anything about how this file system is operating. So this is like one of my last slides, is to say that monitoring is everything. If you don't know how your file system is behaving, you have no way to make informed decisions about it, right? And so we finally deployed Graphite and Grafana as the graphical thing. We're writing our own stuff based upon like the MD stat, the block read write. So that's what you can see, the top graph, the middle graph, and the bottom graph. So what's going to be really advantageous for us in the future is that when the block read writes all of a sudden say, look, there's a bunch of 4K and small little writes happening, we can go to the data mover and look what job it's on in processing. Go to that directory, talk to the person, tar all the tiny files up that are 2 years old or whatever, and then fix a lot of our throughput problems. Okay, so in summary, testing is really key, even for the big guys when you get these appliances that you roll in, okay? Little bitty things. One simple thing that we didn't even think about that was suggested one time, we run our own DNS setup, so everything's on DNS. If DNS is slow to return, that can cause CoreSync to have a problem. So have all of your node names in your host file, like all of the stuff that's inside of your Lustre setup. When doing really, really fast IOPS and read writes, your IB topology really matters. You really have to have a clean setup. And in an academic institution that grows incrementally, right, that's very difficult. There's simple things like we were buying leafs to go in the core switch one at a time. They need to be 4, and you need to turn. We essentially have to go through a quarter of our stack now and unplug things, turn them this way. So they're eliminating a set of blocking that's happening. And then let metrics drive the design, right? Don't do it the other way around. Don't design something because you think it's going to work that way. Definitely get metrics to play an important role in the way you design your thing, your setup. So that's it.
Okay, we're right at time. So if you've got questions, Pastor him offline. Thank you very much for the talk. Have a good one.